12th Periodic Motion. 12.1. Introduction. Vibrations are all around us. Vibrating air carries sound to our ears. Vibrating electromagnetic fields provide light for our eyes. Vibrating atoms give a feeling of heat through our sense of touch. We depend on vibrations in our everyday life, yet many people are oblivious to them. We also use vibrations to make our lives easier. Precisely controlled electronic vibrations in the form of radio waves speed communication. Microwave ovens generate electromagnetic vibrations that force water molecules in food to vibrate, heating the food quickly. Clocks depend on regular vibrations to show the passing of time. The repetitive motion of an engine's pistons produces the energy needed to move a car. 12. A simple harmonic motion. 12.2. Describing periodic motion. Vibrations are repetitive motions. For example, if you pluck a violin string, it will vibrate many times. Motion that repeats at a constant rate is called periodic motion. Figure 12-2 shows a laboratory mass attached to an ideal spring hanging from a support. The oscillation of the hanging spring mass system is an example of periodic motion. Initially, the mass is attached to the spring and allowed to hang at rest. At this position, the force of the spring pulling up on the mass equals the force of gravity pulling down on the mass. Since the mass is at rest, this position is called the rest position or equilibrium position of the system. Note that this is not the equilibrium position of the spring alone. When the mass is attached, the spring is stretched downward until an upward force equal to the weight of the mass is developed, according to Hooke's law, by the spring. To begin the oscillations, the mass is pulled down to y equals -a. Here, the upward force of the spring is greater than the force of gravity on the mass. So when the mass is released, it is accelerated upward. When the mass reaches the system equilibrium position, the forces on it are again balanced. So at this instant, it experiences no acceleration. Newton's first law. Velocity is maximum as the mass passes through the equilibrium position. After it rises above the equilibrium position, the spring force continues to decrease, while gravity maintains a constant force on the mass. The net force on the mass increases in the downward direction and decelerates the mass until it comes to rest at y equals +a. The net force then propels the mass downward. The mass again travels through its equilibrium position at maximum velocity, and the increasing spring force finally draws the mass to a temporary halt at y equals -a. At this point, the cycle starts over again. The mass will continue moving up and down forever in the absence of frictional forces. However, in the real world, frictional forces are always present. A spring may oscillate for a long time, but it will eventually stop. The effect of friction is called damping. See section 12c for a discussion of damped oscillators. One reason the mass keeps moving is that the net force on it always tends to return it to its equilibrium position. Below the equilibrium position, the upward pull of the spring is stronger than the downward pull of gravity. Above the equilibrium position, the spring's pull weakens, and if the mass passes the spring's rest length, it even changes to a downward push. Thus, the net force on the mass always tends to restore the mass to its equilibrium position. The force is therefore called a restoring force, Fa. Often, two or more forces must be added to find the restoring force. 12.3 Characteristics of simple harmonic motion. There are many kinds of periodic motion, but periodic motion that is controlled by a restoring force proportional to the system displacement from its equilibrium position is called simple harmonic motion, SHM. The restoring force in simple harmonic motion is described by the formula F for x equals -k delta x, 12.1, where k is a constant and dx, or dx, is the displacement of the system from the equilibrium position. Notice that equation 12.1 is identical in form to Hooke's law, so a spring mass system can approximate simple harmonic motion in the absence of friction. Many natural systems involving periodic motion approximate simple harmonic motion. The following table summarizes the relationships during simple harmonic motion between restoring force, system velocity, and acceleration. Simple harmonic motion is different from the straight line or circular motions that you have studied. One characteristic of simple harmonic motion is that there is a maximum displacement from the equilibrium condition. The mass on the spring never goes farther from its equilibrium position than it was originally pulled, and a pendulum never rises above the height from which it was originally released. This maximum displacement is called the amplitude A. An object undergoing simple harmonic motion goes from a distance A on one side of its equilibrium point to a distance A on the other side of its equilibrium point, and then back again. The mass in Figure 12-2 repeatedly goes through the same set of motions, from negative A to 0, to positive A to 0, to negative A. This set of motions is called a cycle. The time that the mass takes to complete a cycle is constant. For example, if the mass moves from negative A to negative A in 1 second, the next time it moves from negative A to negative A will also take 1 second. This time is called the mass's period. You studied the concept of period in Chapter 7 in association with planetary orbits, another form of periodic motion. Sometimes you want to know how many cycles the mass will complete in a unit of time. This is called the mass's frequency, F, and is usually measured in cycles per second, or hertz, hertz. A hertz is defined as follows. 1 cycle per second equals s to the power of -1 equals 1 hertz. Since frequency is the number of cycles completed per unit of time, and period is the amount of time needed to complete a cycle, frequency and period are reciprocal quantities. In symbols, F equals 1 over T and T equals 1 over F. 12.4, reference circle. Circular motion is similar to simple harmonic motion. Some aspects of an object's position in simple harmonic motion are related to position in circular motion. Figure 12-5 shows a ball rotating in a circle at a constant speed on the end of a thin rod. Light shines directly on the rotating ball from the left, casting the ball's shadow on the wall at the right. The shadow moves as the mass in Figure 12-2 moved, from a central equilibrium position down to a maximum amplitude, then back up through the central position to an upward amplitude, back down, and so on, as long as the ball is rotating. In fact, the motion of the ball's shadow and the motion of the spring mass system can be synchronized. This helps to analyze the mass's motion. Assume that the mass of the ball equals the mass of the spring mass system. When the motions of the ball's shadow and the mass are synchronized, the mass's period equals the ball's period. If the ball's speed around the circle is v sub t and its orbital radius is er, then t squared circumference, tangential speed, 2 pi r over vt, 12.2. In Figure 12-6, the magnitude of the restoring force, Fr, that seems to act on the shadow is equal to the x component of the centripetal force, Fc, on the ball, assuming the x-axis is oriented vertically and no other external forces act on the ball. The triangle formed by Fr and Fc is geometrically similar to that formed by dx and r. Therefore, fraction r over dx equals fraction c over r, or fraction r over c equals dx over r, 12.3. But Fr equals k delta x and Fc bundir mac frac star eit. So, combining these formulas in equation 12.3, k dx mvt 2 r hertz dx r, or kr slash mvt to the power of 2 equals 1 slash r, 12.4. By rearranging equation 12.4, you can see that R2 jotchers VT2, M, K, or RVT harsh, root M, K, 12.5. Substitution of the right side of equation 12.5 for RVT in equation 12.2 gives T chari 2, pi r over VT equals 2, pi r over VT. Or T equals 2 pi root meters per kilogram, 12.6. You can now calculate the period of the spring mass system's motion without constructing a corresponding circular motion diagram. The period is proportional only to the square root of the oscillating system's mass. If the quantity k is considered a constant, that characterizes the elastic property of the system.